Hello everybody, welcome to the next video in the series of Physics at Home. Today we're gonna look at the part 2 of Kirchoff's laws. Last week we looked at voltage law or the loop rule, right? And this was the circuit that we used. Today we're gonna use the same circuit, but we're gonna change it slightly bit. So the same resistor 1, resistor 2, but we're gonna add a third resistor. This is going to be connected between points E and F. Okay, same voltages, slightly different V2 now today, but we'll see. So the circuit looks like this. R1 is here, R2 and R3 in the middle. So for now, let's look at the values of R1, R2 and R3. I'm going to mark them here. 55.6K. $74.4 and in the middle 91.2. Alright, so 91.2 kilo ohms. Okay. The two batteries. Okay, so let me just check their voltages. 8.6667. Okay, let me write this down. 8.66 volts, and voltage 1 is 6.36 volts. Alright, so 6.36 volts. Alright, there you go. Now let's connect them. But here's the thing. Last time we looked at loop rule. Now we're going to look at a junction rule or the current law. So junction is something like this, that it's like a T section here, right? T section. And currents are flowing in each one of these branches, right? So for example, if the current is flowing in this direction and this direction, then they're going to add up and become a total current. Sum of the two would leave like this. Okay. Now this is just an example here. What the junction rule states that the sum of the total current at a junction is 0, meaning the total current entering is equals to the total current leaving. All right. Now in this circuit here, I don't know, what are the directions of the currents in each branch. Okay, so this is the left branch, the right branch, and then the middle section, right? So I don't know how the currents are flowing, but we can, connect them, and the multimeter will be able to tell us, how much and in which direction is current flowing in each one of these sections. Okay, so let's hook them up. Alright, so the positive here of the battery, 9 volt, to the negative, correct? So positive to negative. Alright, so positive to negative. Okay, so we have that. Then positive of the 6 volt to resistor 1. Okay, so resistor 1. Yeah. Now from resistor 1 to resistor 3 here, the two ends are connected. Yeah. Alright, so again, so R1 to R3, and then here we're gonna create that junction, right? F. So this is the point F. Okay. So from here, then over here. Okay. And then from here it goes to the negative of 9 volt. This is the point D. Alright, we have that. And the last thing that we need to do is connect the, so this is the E, right? So E here, so this resistor is supposed to be connected to E, it's a junction E. Now remember again, this whole, this white cord is this top line here, right? The conducting wire. So it doesn't matter, where we hook up this end of the resistor. We could hook it up here or we could hook it up here. It doesn't matter. It will create a junction E as we see in the picture. Okay. So let's do that. Alright, so from here, now connect here. There we go. Alright. There it is, the circuit. Okay. So A, B, C, D, and then E and F. Right? Sorry, E and F. Yeah. Now, current is currently flowing, in each one of these 3 branches, right? So this is the left branch, this is the middle, right? And this is the, this is the right branch, correct? So now we want to know how much is and in which direction is the current flowing in each one of these. So to, measure the current, we have to disconnect, let's say in the left section, if you're doing, we have to disconnect, either the red cable here, which is, resembling this part, or the yellow, this yellow here, which is resembling this part. So I'm going to disconnect the red cable. Go to the current here, right? So I'm in the micro region, and as we said, we don't know if the current is flowing from, from B to A or A to B. Okay, so B to A would mean that, it's coming out from here but going to positive. But since this is a positive here, I'm gonna make a assumption that probably the current is going from leaving 6 volt and entering to the resistor 1. And so what that means is the red probe here needs to sit here so that the current is coming out and then going through the multimeter, and it's gonna enter here, correct? And that's what it is. I think it was a good assumption. So 113.8. If my earlier assumption was maybe leaving from the resistor and entering here, we get the same number but a negative sign, correct? As you can see on the multimeter, negative sign would indicate that the way I'm connecting them needs to be switched. Okay, so just like it was before. There we go. 113.8, and it's micro. Okay, so let's write that down. So current is moving in resistor 1 in that direction, current 1. 113.8 microamps. Okay, 113.8 microamps. So let's connect this back since we had disconnected this wire. Okay. Now I want to know how much is the current in the right section. Okay, so I'll leave this here. So in the, through R2, how much is the current flowing? To do so, now I'm going to disconnect the black cable. Okay, so since negative is here for the voltage 2, right? So this is the negative is here. So I'm assuming now that's all, it goes negative to positive. So meaning the current is flowing in this direction. Okay, so from R2 it leaves and then goes to the negative of the battery here. So let's see if that is correct. So leaving means, this would be, now enters the input here, right? The red cable, and then goes here. Looks like it was correct again, since it's a positive number. So 114.5. Okay. Excuse me. So current 2 is in this direction. I2, 114.5 microamps. Yeah. All right, so let's go ahead and connect this back. Now we need to figure out, now we need to know where is the current flowing in R3, right? So if you look at the picture here, okay, current 1 is entering, current 1 is in this direction, right? So current 1 enters here, I1 goes to the junction F, correct? Current 2 is leaving in that direction, correct? Because it is going in that direction, right? Clockwise, counterclockwise. So I2. Now I1 is 113.8 and I2 is 114.5, right? So what enters is not equals to what has left, right? We are getting more I2 compared to what is entering. What this means, and the only thing that this could mean, is that current in R3 has to be flowing in this direction. Current 3, I3. So that, the difference between the two has to be the current I3. So this I3 and I1, they meet and I2 leaves. So what is that? So 114.5 minus 113.8, so it's about 0.7. I am expecting this to be some number about 0.7 microamps is what I'm expecting. Now let's see if indeed that is true. Okay, again the current is coming from the junction E, right? So junction E to R2. So let's see if that is correct. Again we have to disconnect. And let's see if everything is okay. So it leaves here. So my red probe has to go here and my black probe has to come here. Okay, so you can see now I'm getting about 0.5 microamps. I was expecting maybe 0.7 or 0.6, somewhere like that, right? But it's 0.5. Okay, it's close, it could have been better. But two things, right? First of all, definitely the current is going in this direction and it's close enough number here, right? So the junction rule works. We were given 2, we measured 2 and we predicted what could have happened with I3, right? So exactly what is going on, right? So it's leaving there and entering here. Yeah. All right. So now that we have all of these three, in the next section of the video, I'm going to show you how we can prove indeed that is happening, okay, using the loop rule that we learned last week. On the left here, we see two tables, and these tables are the actual measurements that we performed, correct? So these are measured values. Both of these tables. And on the right, we see the circuit. Now we said that we're going to prove that indeed in the R1, R2 and R3 the directions and the values of the current are what they measured, what they turned out to be. Okay. Now to do so we're going to use loop rule. Now before we go there, let me just bring up a situation where let's say that we did not know or we did not have the tools to figure out the actual current values and in the directions of the currents. Then if we had to theoretically calculate it, how would that go? So what I would do in this case is that let's say that voltage 1, so we know that positive is on the left side. So then I would assume that maybe in the left section here the current is flowing in this direction. Okay, so current 1 is like this. Okay, in the right section here the V2, again the positive is on the left side, so I would assume again here the current is flowing in this direction. So that's what I would do. I'll call this as I2. Okay. So I1 is entering and I2 is leaving. Now our current through R3, it could go up or down. Now we already saw that current is going from E to F, right? But what if we did not know? Okay, then I'm gonna at this point of time purposely I'm gonna make a wrong assumption that in R3 let's say the current is going in this direction. Okay, I3. So what this means is that when I3 and I2, when they meet, they're gonna add up and go out as I1. Yeah, so this is I3 and this is I2, right? Again, this is a wrong assumption about I3 based upon what we understand already, but again, assuming that I did not know that current in R3 in which direction it is. So given this situation here at junction E, now looking at the current law, the sum of the current at a junction is 0. What this would mean then, I1 equals to I2 plus I3. Okay, now I'm going to use this information now later on in just a few minutes. Now let's invoke the loop rule. Okay, so what I'm going to do here now, create two loops. So the loop on the left, okay, so I'm going to call this as loop 1. Okay, so for the loop 1, let's say I begin at E, then I go left, right? So there is voltage 1. Okay, so the voltage 1, as we are going from left to right, and if we recall the sign convention here, so if our travel direction is from negative to positive, you add the voltage. Okay, so voltage 1. Then come to A, turn down, and then I'm gonna hit R1, right? So if we look at now here, then if the direction of your travel, the green arrow, and also the direction of the current is the same, then the I times R, the voltage drop across that resistor, has to be subtracted. So meaning now the I1 R1, that multiplication has to be subtracted. Okay. Now I come at the bottom, B, turn right, hit F, right? Now hit F and then I start going upwards. Now our assumption is I3 is going upwards, right? So I3 times R3 also has to be subtracted because it's in the same direction as the travel, right? And we come back to E. So all of this then becomes 0. Yeah. All right. So now let's plug in the values here. So 6.36. So this is V1, correct? Minus, let's say we don't know I1, correct? But we know resistance 1, so which is 55.6 into 10 to 3, right? Minus I3, and then R3 is 91.2 into 10 to 3, correct, equals to 0. Alright, so we have I1 and I3, and at this point of time what I'm going to do is I'm going to utilize this junction rule that led us to I1 equals to I2 plus I3. So I2 plus I3 I'm going to plug in as, I1 here. So 6.36 minus I2 plus I3 times 55.6 10 to 3 minus 91.2 10 to 3 I3 equals to 0. Okay, so this 55.6 we're gonna distribute equally as we're multiplying it. So this becomes 6.36 minus 55.6 10 to 3 I2 minus 55.6 10 to 3 I3 minus 91.2 10 to 3 I3 equals to 0. Okay, so we have I3 here and I3 here. So these two numbers, the 55.6 and 91.2, they both have same signs, so they add up. So what do we have now? 6.36 minus 55.6 10 to 3 I2, and then 55.6 plus 91.2, that is 146.8. So again, negative sign carried forward, right? So negative 146.8 10 to 3 I3 equals to 0. Okay. Now what I'm going to do at this point of time is I'm going to move the 6.36 to the right. So if 6.36 comes to the right, then it becomes negative, correct? And each one of these terms then becomes negative. That negative number I2 minus negative number I3 equals to negative 6.36. And I can multiply all of these terms by the same number, left side, right side, by negative 1. Then that will give me positive values for each one of them. So what I end up with is 55.6 10 to 3 I2 plus 146.8 10 to 3 I3 equals to 6.36. Okay, this is my equation 1 for loop 1. Okay, now I cannot solve this further because I don't know I2 or I3, again theoretically speaking, right? Now what I'm going to do is I'm going to now take a look at loop 2. So the loop 2 is this way. It does not matter if I, go in the counterclockwise or clockwise direction. It absolutely does not matter. Because if we do other way, then the signs, just change. Correct? Each one of them will have an opposite sign of whatever they were assigned in a counterclockwise direction. Alright, so let's look at loop 2 now. So in loop 2, we start at D and we hit V2, right? So it's V2. Then we come to point A, the junction A, then go down. Now look at this here. We are traveling downwards, but the current is I3 is upwards, right? So which is this situation. At the bottom, if you can see the sign convention, that if the travel and the current are in the opposite direction, you add the I times R. So that's what we have to do. So times I3 plus I3 times R3. Yeah. Now we come to the bottom here, F, turn right, hit C, then start going up. Now the travel and the current are in the same direction, so we have to subtract. So minus I2 R2 equals to 0, right? Okay, so now V2 is 8.66 plus R3 is 91.2 10 to 3 I3, right? And then minus R2 is 74.4 10 to 3 I2. This is equals to 0. Now the same thing that we're going to do excuse me, to what we did to equation 1. I want the I2 and I3 on the left of the equal sign, and the number, the constant to the right. Okay. So this now becomes the 74.4 10 to 3 I2 minus 91.2 10 to 3 I3, and it, as you can see, I'm switching the sign for each one of them. So then 8.66 would have been negative on the left side, right? Left side of the equal sign. But if we move it to the right side, then it becomes positive 8.66, right? So that's what I'm going to do. Equals to 8.66. So now look at these. So we have two equations, equation 1 and equation 2. Both have the same exact, unknowns, the I2 and I3. So two equations and two unknowns. If we recall, in algebra, that is the system of equations, right? And there are multiple ways of solving this. Manually you can, use the substitution method, or you can use the addition method, any way you want. Okay. If you have a calculator, a scientific calculator that is, already pre-programmed to solve system of equations, all you gotta do is plug in the constants here, because these are they look like, a1x plus b1y equals to c1, and a2x plus b2y equals to c2. The calculator would ask for the a1, b1, c1, which are the 55.6, 146.8, and 6.36, correct? Again, don't forget 10 to 3, and a2, b2, c2. If you enter that, calculator will calculate and then tell you what are the x and y. Again, x here represents I2 and y would represent I3. What I'm going to show that, let's say you don't have any of these tools at disposal, but you do have internet, then we're going to go to a website called Wolfram Alpha. And on that website, they have a program where all you got to do is type out the equations and it will calculate the x and y values, which would be our I2 and I3. Okay. So let's see how that goes. Okay, so here's the website, Wolfram Alpha. And here on the front page, on the search bar, you can type in system of two equations. So click that and it would open up this page here. What we need to do is, type out the two equations that we have, and instead of I2, I3, just type in, x and y. Okay, so here in my equation was equation 1 was 55.6 10 to 3, right? So 55.6 exponential 3 x, correct, plus 146.8 exponential 3. Now that was y, right? So I3 equals to 6.36. That is equation 1. Equation 2 is 74.4 exponential 3x minus 91.2 exponential 3 y equals to 8.66. Okay. And there you have it. Okay, so we have typed out our I2, I3 equations as these, and then we say compute. And there we have it. Okay, so we're gonna get the values for x and y. Okay, so it's gonna give you an approximate form here, correct form, like a ratio. But if I could also have it as an approximate form, so I could click on it and I'm gonna say more digits. Okay, and there you have it. Okay, So the first number is 0.000157, right? So there are 1, 2, 3, 4, 5, 6. So 115.7 10 to negative 6 micro, right? Microamps. That is the current 2. And Y was supposed to be I3, right? And I'm getting a negative 5.197 10 to negative 7. I'm going to write these numbers down on a piece of paper here. And we're going to go back to our PowerPoint again. Okay. So this is how you can use the Wolfram alpha to solve a system of 2 equations. Okay. So now that we saw how to solve system of equations there, I just cleaned up all the writings from the slide and put them in a nice equations here. So the loop 1 gave us this equation, and loop 2 gave us this equation, right? And after solving, we have these values, the I2 and I3. Okay. So let's look at I2 here. Okay. So I2 115.76. This is what based off of these values, right? Based off of the just the voltage and resistance values, we calculate the current I2. When we actually hooked it up earlier, created the circuit, that I2, the current through 2 was 114.5 10 to negative 6, right? So you can see it's pretty close, very, very close to the number that we, expected to be. I3, well, before I go there. So now, not only that, but, the number came out to be positive here, right? So meaning the assumption while solving it, right, this direction of the current I2 is correct. So that's why the number came out to be positive. Now look at I3. I3 here is negative 5.197 10 to negative 7, which is, negative 0.52 10 to negative 6 amps. This number is again close to the current through R3. Yeah. Except for the fact that there is a negative sign here. Now, this negative sign is going to indicate that the assumption that I made earlier, the I3, which was incorrect. I3 is supposed to be going downwards. Let me use the correct color. So I3 is supposed to be going downward. And indeed, it was true, right? So E to F, that's what we measured. So it's going downward. So I2 comes here, right? And then I3 leaves. Yeah. So I1, our assumption earlier was that I1 equals to I2 plus I3, right? So given the actual values that we have, now we can figure out I1, which is I2 was 115.76 10 to negative 6 and minus 5.197 10 to negative 7. Yeah. So now this gives us, let's see, okay, so 115. Yeah, so it gives me about am I doing this correctly? Yeah, 0.52. Yeah, so 115.24. Okay. So I was expecting 113.8, so 114, but I'm getting 115 from here, right? So this number and this number here, excuse me, they are close enough, right? So again, looking at the actual values, from solving the equation, that gives us the I1 based on our earlier assumption. Now we have the current value for I1, and also it's coming out positive, meaning, the assumption for this I1 direction is also correct. Okay, so I1 and I2 were correct, but the I3 was incorrect. So now we have fixed it. And if we look back now, then it does make sense that, the I2 was entering and then I1 and I3 were leaving. So indeed, actually, the correct way of writing this down would have been I1 1 plus I3 equals to I2. Yeah. So now that we know, we can see all of these, we can easily calculate the percent error, for example, between the expected value and the actual value. Yeah. So there you have it. This is how we can test and verify junction rule. Okay. Next week we are going to look at resistors in series and parallel. Have a good one.